Hi everyone, I welcome you to this session. I am Dhanyata from NISB and I am CAS Secretary for the year 2021 and 22. So without wasting much of our time, let's get started. So as the name suggests, we'll be dealing with the software named LTspice today. So our today's agenda is as follows. We'll be dealing with the introduction to LTspice. We'll get to know the components and the various type of analysis that is present in LTspice and how we can use it accordingly. We'll be also building two or more circuits, namely half wave and full wave rectifiers. I hope many of you have dealt with OpAmp circuits, as in operational amplifier circuits in your first or third semester. If not, don't worry, we'll cover it. Here comes the interesting part of today's session. It's inverter and 60 SRAM cell. You'll get to know more on what SRAM cell actually is and how you can build it on your own. So, general question is what exactly is LTspice? So, LTspice is analog electronic circuit simulator, which one can use to design, analyze, and improvise the circuit design he or she is building. Say, most of the circuits which you have come through is already inbuilt. There is nothing much you can do on it. Say, somebody has built any circuit and you're just analyzing it. Consider simple RC circuit or resistive circuit. You just have voltage and resistors. The basic operations you perform are KCL and KVL, and you find out what the parameters are. So those are the basic thing which you are limited to. But later in college life, you come across situation where you're given to design an amplifier from scratch. At that particular time, there comes a situation where you can't solve circuit completely on your own. You'll have to experiment it a little. You will have to do fewer more trial runs. There are cases where you won't get any output. Say the output becomes zero. So if you try solving it on your own by paper pencil method, you won't get the exact solution. So what people have come up with is they build software such as LTspice. They give it handy to you, and you can make use of these simulators to design your circuit and improvise it later. So you might be thinking, is LTspice the only one which we can use to simulate our circuits? In that case, no. There are other simulators like eSIM and Tina TI. For today, we'll be dealing with LTspice. This is how the software looks when you first install and open it for the first time. So this obviously doesn't look good. So let's change it. As of now, our workspace is empty. See, you can see all the icons here are disabled as of now. That's because we don't have our workspace ready yet. So to create a new file, you need to go under File, New Schematic. Now the workspace seems neat and the icons are even visible. Let me brief you through the icons here. I am sure most of you have used your breadboard. The most important things which we use on breadboards are the components such as resistors, batteries, and wires. So when talking about wires, this is the symbol for wire. This is the icon for wire. In order to connect to components in LTspice, you would make use of this icon, the pencil with a line there. Everyone knows that a circuit is incomplete without ground. This is the ground symbol. We'll be using it in most of our circuits. Not most, all of our circuits. Say you have three or two loops in your circuit. You're confused whether which loop is what. Say if you wish to name your loop as A, B, and C, you can make use of this label net here, name them accordingly. Most of the basic components which we'll be using are resistors, capacitors, and inductors. They are here accordingly. So resistors, capacitors, and inductors. And another important component which we'll be dealing later in the session is diodes. You might be wondering, say, these are the only basic components which I have. What about the other components? So this is the icon for a component. If you just double tap on it, you would arrive at an interface such as this. By scrolling, you would get the name of all the components listed here. If not, if you know some component by heart, you can just type in it. See, voltage, I need voltage. If I type voltage, the symbol appears, and if I click enter, my voltage is here. So you can drag it anywhere in this workspace, and if you select this particular place, you just need to go there and then just tap it once, and your voltage is fixed there. Say if your circuit consists of more than two or more voltage source, you can place them accordingly here. See, as of now, we don't need voltage sources like this. So in order to get rid of this redundancy, we'll just click escape, and we are gone. So I don't need these extra voltage source also. So what I'll do is that I have a symbol known as scissors here. So I'll just click on it, and I just bring it towards the component which I want to be deleted. So I'll just click on it, and it goes away. Click and it goes away. So in this manner, if you want any of your component or any of your extra wires to be cut, you can use scissor symbol here. And again, in order to get out of this, you need to click escape. Next, let's try adding some resistors here. Let this be in parallel with the voltage source. Say the alignment of resistor is not as expected for me. So if I want to tilt my components towards left or right, what am I supposed to do? The simple command for rotating the components are control plus R. See, the component gets rotated. Again, if you want it back, control R, gets rotated. Again, if you want that to be rotated, control R. See, so simple. Let me place it here. So again, I don't need the third resistor as of now, so I'll just delete it. Everything seems fine, and we are forgetting something, that is ground. Every circuit you build, you need to connect a ground to it. Seems good for me. So let's connect all of our components by wire. So we need to click on wire, and then see, LTspice is very useful in drawing wires. It gives you arrangements, pre-built arrangements. Say if you the I hope the blue square is visible there. If you just go on blue square and just click on it once, the wire gets drawn. And then in order to move from here to here, you need to click somewhere here. See, you need to click here again, a tap, and then tap again from this blue square to other end of the R1 resistor. Tap here, then go down, tap here, and then you need to do this accordingly until all of your wire gets connected. And in order to get rid of this, just click escape. The dark blue square here symbolizes that your all of your components have been connected successfully and your circuit is ready. Simply connecting these components and leaving it as it is doesn't make any sense, right? So we'll try adding some values to it. Before adding any values, you can observe that it's mentioned only v here. Let's add some value for voltage, 10 or 30. Any value which you prefer is good. So I'll prefer giving 10 volts of supply. So I'll just give 10 volts and then enter. So now my circuit is supplied with 10 volts of DC voltage. Let me add some value for this resistors. Say to add any value, again double tap on it. Then say I'll give it as 1K. Let this be 2K. So our circuit is now ready. So yeah. If you even desire to name your circuit with some unique name, and you want that name to appear somewhere in this workspace, you can do so by clicking on this text icon here. You can type in the text you want. As of now, let this be demo circuit, and then just click enter. The name comes. You can just tap it anywhere you want. Demo circuit. See, this is how you name any circuit in LTspice. So the easiest way of finding all the circuit parameters using LTspice is as follows. Just follow these rules. In order to simulate your circuit, you need to go to simulate command, and at the end you can see something known as edit simulation command. So there are more than two types of simulations. Not more than two types. There are many types of simulations which LTspice provides you. Among them are transient analysis, DC analysis, AC analysis, and operating point analysis. We'll be dealing with one such command known as operating point analysis. So DC operating point, you have all the analysis listed as mentioned as seen here. So move to the last column, that is DC operating point, and then in order to select that command, you need to click OK and place it somewhere. So now your circuit, you built the circuit from scratch, you have given the values to your components, and then your circuit is ready for simulation. Once you are ready with all of these commands, you just hit run, and there you go. You get all the circuit components values. See the current flowing in resistor R2, the current flowing in resistor R1, and the current across the voltage. You might seem that this is inaccurate because of the minus symbol there. That is actually corresponding with the flow of current, the direction of current which you assume. That depends on the minus sign. Rest of it is fine. Most often you would get the correct answer here. The only thing that varies is your sign, not just the values which I have mentioned here. You can try out with other values such as 30, 10k, 50k, any values which you prefer would be right. So this is one basic circuit just to show you that how the analysis could be done.
Moving ahead, we will be going through the rectifier circuits. Before going into that, can someone tell me what exactly is rectification, since we all know it from our school days? Okay, I just guess that you are just not willing to answer. Let me make that simple. Yeah, exactly what you mentioned, Anusha. It is a process in which you convert the input AC waveforms into DC waveforms. And we know that basically rectifiers are of two types, that is half wave rectifier and full wave rectifier. Since I just hope that most of you know the working of this, so I will be just briefing you how exactly that works. So as the name suggests, half wave rectifier just conducts half of the input cycle, so that whenever you see the output, it will be just 50% is converted. So how does this exactly work is can be easily analyzed by knowing the working of the diode. So we all know that for a diode, if we apply positive voltage on the p side, and when the voltage on p side is greater than n side, it acts like a, it acts like a closed circuit, and it is forward bias, because of which it entirely conducts. Whereas the other thing happens, whenever the voltage on the p side is less than that on the n side, it acts like a open circuit, since it is reverse biased. So, having this knowledge in mind, let's move ahead. So, during the positive half cycle, as I mentioned, the diode is forward biased, because of which it acts like a closed circuit, and whatever input which was applied at that time is reflected as the output. Whereas coming to the negative half cycle, the PN junction diode will be acting like a open circuit, because of which the circuit is not at all complete, right? So there won't be flow of any current, and hence you won't be able to see any output across the load resistor. So this is how exactly a half wave rectifier works. Let's move on to what exactly is the theory behind full wave rectifier, and then let's go for building the circuit. So the full wave rectifier, we know that there are actually two types. In two ways, we can build that out. One is the center tapped rectifier, and the other one is a bridge rectifier. In this session, we will be dealing with the bridge rectifier. As you know, there are four diodes which are arranged in a bridge manner, and the working of this is exactly similar how you analyze the half wave rectifier. So whenever you apply the positive half voltage here, if you can see, it is the D1 and the D2 will be forward biased, and hence it conducts. So let's just look into it. So the D1 and D2 will conduct whenever there is positive half cycle, and hence there is a closed circuit, because of which current and hence whatever input voltage was there will be reflected at the output. So during the negative half cycle, the other two diodes, that is D3 and D4, will be conducting, because of which whatever was there in the input is reflected as output, and it is inverted in nature. So you will be getting a pulsating DC output. So now let's get into LTspice and build this out. By the way, we will be not building half-wave rectifier, and we thought that it would be good to mention why we are not doing and what exactly is happening. If you are able to find it out, we would be really happy, and you can just share us your info. This is how we all know half a rectifier looks like, right? So but when we did the simulations for this, so just sensing the input just comes out to be fine. Whereas in the output, we should have got like all the positive waveforms should have been appearing. But in this case, it's not exactly happening what we like learned theoretically. We were unable to find it out what exactly is happening, and we just thought of like mentioning it to you. Maybe we can consider this as a drawback of the LTspice itself. So moving ahead, just open a new schematic, and we will be building a full wave rectifier. I hope that there are no doubts. So for building a rectifier, we will be in requirement of a transformer. LTspice doesn't directly offer a transformer, so we have to couple two inductors. So let's do that. And you can just rotate it by pressing Ctrl R. We will be requiring an input voltage which can be selected from the components. And we will be in need of 4 diodes, as we just saw it in the slides. And we will be requiring a load resistor. We have just kept 2 inverters, but this is not exactly a transformer yet, so we have to make some modifications to this. So this can be done by including a spice directive, where we will be mentioning the coupling constant of the the transformer that we are using. We will take it to be as ideally 1. So just type in as K and the name of the inductors that you have selected, and mention that as 1. And you can just place it up here. So when you place this here, you will be getting 2 phase dots, by which we can confirm that this will act as a transformer. And one more thing that we have to specify for a transformer is the number of turns that is on the primary and the secondary side. And we know that in our labs, we do have used a step down transformer. So we will be implementing the same thing here as well. In order to write the values, just right click on the component, and you can just type in. And if you want to drag the components, you can just use the move button and just select it. And we will be requiring the ground. So now let's start connecting this one. You can easily connect it by just dragging and dropping it at the right positions. So in the secondary transformer, one end is both the ends are connected to this bridge network. And the bridge network, in turn, one of its end is connected to the resistor. and the other end is grounded. This is how a full wave rectifier could be built. We can even specify the diode models also. So for that, you just right click on this and you just select here, pick new diode. In this case, we will be using 1N4148. You are free to use anything according to your specifications, and just make sure that you select it for all the diodes. Okay, that's pretty much done. So yeah, I did forgot to mention the value of the resistor. So you can just take it as 1 kilo ohm. And the voltage thing, we will be taking it as a sinusoidal waveform. So you can just select here the sinusoidal waveform, and we'll be taking the offset to be as 0 and amplitude are 10 with 50 hertz frequency. And in order for the perfect working of the transformer, we need to mention the parasitic resistance as well, so that we can just take it as 0.01 milli, and you can just press OK. So these details would be displayed up here. In order to run this circuit, we will be doing transient analysis. You can just go to here and mention the time as 0.05. Paste it here. So everything is just set. We can just press the run button here. So we will be just pointing to the input on to the primary side, and this is the sinusoidal voltage with amplitude as 10 volts. And for the output, we will be analyzing it across the load resistor, and we have got the expected output, that is the input whatever it is, be it positive half cycle or negative half cycle, is completely rectified. So this is how a half wave rectifier could be, a full wave rectifier could be built in. We also know that we can add a smoothing capacitor to this circuit, so that it would be like it would be too near to a DC output itself. So let's just add the capacitor to the existing circuit. Just connect a capacitor in parallel to the resistor, and the value of the capacitor would be 5 microfarad. So, and then just save the circuit and you can run it. Yeah, you will be able to see that smoothing effect out here. Yeah, so this is how a full wave rectifier works.
Well, now that you're familiar with the rectifiers, OpAmps are pretty much easy. You might have heard about OpAmps. I guess you have heard it. So this is how a typical or ideal OpAmp looks like. So it has 5 terminals, namely plus and minus VCC, that are nothing but power sources. You have two inputs, namely inverting input and non-inverting input. So as the symbol suggests here, so VN is nothing but negative terminal voltage that you're supposed to apply, and it is also known as inverting terminal. The plus symbol indicates that the input voltage which you're applying is of non-inverting type, and you're applying a positive voltage there. Every circuit has input and the output port. Similarly, OpAmp has output terminal known as Vout. So here are some interesting facts about OpAmp. The why do people prefer using OpAmps? See, earlier days before the computers could arrive, people used to carry out basic operations such as addition, subtraction, multiplication, and division with the help of OpAmps. So that's the reason why people prefer OpAmps, operational amplifiers, over other amplifiers. Even if you apply minute inputs such as 10 millivolts or 100 millivolts, the output would get amplified by 10 power 5 times of the actual input. So that is actually a huge gain. See, you are applying a low signal, and at the output side you're getting a high signal. That is what everyone would desire the output to be. So this is the main reason why people would prefer op-amp circuits. The input impedance of op-amp is infinity, as you all know, and the output impedance is zero. The final output of the op-amp is just the difference between the uh, positive and negative terminals of the op-amp multiplied by the applied input. So let us study about the interesting applications of op-amps. So first one would be, yeah, we'll be building this circuit. So firstly, let's get into the theory part of it. So inverting amplifier, what does inverting amplifier means, and why do we need to build an inverting amplifier? As I mentioned earlier, for the very low input signal, you would get a high output signal. So there might be times where you expect very low output signal, even if the applied input is of say 1 or 2 volts, and you're expecting the output to be 4 or 5 volts. So can it be done using op-amps? If that could be done using op-amps, that would totally contradict my statement, which I mentioned earlier. I said for the minute input which you are applying, you would get a huge output. So how are we supporting the statement of mine? In order to achieve the situation which I just said, that is, say if you are applying 2 volts at the input, and if you are desiring the output to be some 6 or 7 volts, you could do that by adding a feedback resistor here. See, some part of your output gets added to the input. So this is the way where you can reduce the gain of the op-amp, and you can simulate it according to your specifications. So this is one way of doing it, and the other way is obviously the non-inverting type. So what is the basic difference between these two amplifier? In inverting type of amplifier, if you are applying a sinusoidal voltage at the input, the desired output would be also sinusoidal, but the only change is that it would be 180-degree out of phase with the input. We'll see that when we analyze it using LTspice. The difference you would have with non-inverting amplifier is that when you apply a sinusoidal voltage at the input, you would get the same exact sinusoidal waveform at the output. There would be no phase difference between both input and the output waveform. I'll just show you that. Before we get started, just make a note of the output for non-inverting amplifier. It is simply 1 plus R2 here is the feedback resistor, so R2 by R1 times the input voltage, whereas for the inverting amplifier it is negative of R2 by R1 times the V in. Here negative symbol symbolizes that the output waveform is 180-degree out of phase with the input waveform. So without wasting any of our time, let's get started. So open new schematic, you can just type in Control N. So what we need here is op-amp. I don't need voltage anymore. So op-amp, select op-amp 2 here. Done. And we need voltage sources here for giving the input voltage. So again, voltage. Just place another voltage sources here. I'll just tell you why. So as I said earlier, if you are using breadboard, you will also use a 12-volt battery or 15-volt battery to provide power to your breadboard. So our op-amp won't work unless and until you provide an external DC to it. So if we try providing this DC somewhere here, the circuit arrangement is disastrous. You just can't imagine how the circuit would look. So in order to make a circuit simple, let's just try placing our supply voltages somewhere away from the circuit. So after placing your voltage sources one below the other, just try adding some ground here, and we need ground here as well for the positive terminal, and then just click escape. As we saw earlier, we need two resistors. Control R, they get rotated, and then one feedback resistor here, and then escape. So it's time that we connect all our components together. Okay, I missed a ground here. Just click on the wire symbol there. Just a second. Yeah. Perfect. So click on the wire signal here, and place it somewhere above the second voltage source. So just click on it and then drag the line towards the end, and then just leave it. So make sure that all of the three components are connected there. So two voltage sources and ground are connected together now. So let's leave that aside for now and connect the other components. So connect the ground voltage source, connect this with the resistors, connect this to the inverting terminal, and then the non-inverting side of the op-amp is grounded now. Connect the feedback resistor to the inverting terminal. Perfect. So everything seems fine. The only thing that is left is plus and minus VCC. So let's see how we could connect that. You can see the label net here. Just click on it once and then just type in VCC. Then click OK. Place it somewhere here. That is VCC. And you can see the plus symbol here. So that is plus VCC. So just you can see the square box which is appearing below VCC and near the op-amp. So just bring one on the other and then click it. Just press escape. The VCC here and the VCC here gets connected. Connecting minus VCC, just type in minus VCC, enter, and connect here. And this is your minus VCC. So just tap here once. So everything is good. So far, so good. So let's give supply voltage as 15 volts. So your plus and minus VCC are 15 volts respectively. Let the input voltage be of sinusoidal wave. So I hope you got this. So you just right click on this component and then you move to advanced option. There you have various type of signals, namely pulse, sine wave, exponential wave, and many others. So we'll be selecting sine wave. Let the offset be 0. For our simulation purpose, let's keep the amplitude as 2 volts. Let the frequency be 1K or 100 or 50 depending on your choice. So just click enter, and we have given the voltage as 2 volts sine wave with frequency 1 kilohertz. Let the input resistors be of 1K, and let R2 be 2K. Also, this again depends on your choice of values. You can have any number of values which you want. So the expected output, let me remind you the expected output here. The V out would be minus R2 by R1 times the input voltage. So R2 by R1 gives me 2K by 1K, which is nothing but 2, and my input voltage is 2. So 2 times 2 is 4. You're supposed to get 4 volts, which is 180-degree out of phase with the input voltage as your output. Everything seems fine here. Where exactly the actual problem arises is that for every component which we select from LTspice, that would have a predefined model file or the library file. Say if you're selecting a diode, you had something known as 181418, something like that. Similarly, for op-amp as well, we need to have that dedicated module file. Most of the op-amp which we use are of MUAS 741. Unfortunately, LTspice doesn't have model file for that. So what could be done? So scroll down a bit, and then design and development. I hope this interface is available at your PC. Just click
Yes.
on this link, download. You need to download this particular file. So just click download, and that gets downloaded. You need to extract that somewhere on your computer.
Yeah, cool.
Right. I'll show the extracting thing also. Just a second. Okay. Extract to. Let me extract it here again. Okay. So the extracted version appears here. So I'll just double click on it, and then I enter this surface. So I hope everyone are following with me. I'll demonstrate a bit in a bit slower pace. So I'll just right click on it, and you need to open that with the Spice Simulator schematic capture. Just click on it. You need to select LM741 bar NS, Control C, and then go back to the circuit where you actually build it. Here you would have something known as OpAmp 2 or some random name. Just again right click on it, and then you need to paste this LM741 bar NS and just click enter. So your OpAmp gets name now. I'll just remove this. I'll demonstrate again. After giving the OpAmp a desired name, you need to go to spice directive, and then you need to type in dot include space. Go back to the place where you had downloaded the extracted file, then copy the file path, then go back to the circuit, Control V, paste it, and then again backslash LM741 dot mod, paste it here. That's it. Now the model file is imported, and your circuit is ready for simulating. For this particular analysis, we'll be using transient. So edit simulation command. Stop time, let's give it as 5 milli, and time to start saving data. We want the data to be saved from the time 0, from the initial time, and let maximum time step be 1m. If you give just dot tran and 5m, that's more than enough. These are just we are briefing the LTspice on what are the particular specification which we need during this operation. So just click enter, place it somewhere. You have the run command here itself, so just run it once. Okay, let's close the yes. Okay, I've missed some part here. So after building your circuit, you need to save your file somewhere. So save as inverting amplifier, and then just click enter. So save your file and then just run it once. So this looks awkward, so let's change it. So as explained earlier, our output should be 4 volts, which is 180-degree out of phase with the input. So input, let's check if it's correct. So yes, we are getting 2 volts. It's sine wave, and okay, I messed up here. You need to add a label here. Say V out. Our V out comes here. Let's do this again. Let's run this. We'll change the window, and then our input is correct. Perfect. Our output is 180-degree out of phase with the input, and we have it as 4 volts. Similarly, we'll try building the non-inverting amplifier as well. So if you want, you can take the screenshot of this, write on later. Yes, I need this to be saved. So control and new file. So since you have got the knack of building circuits in LTspice, we'll just build it very fast. So first we need to select, okay, let's start with voltage itself. Voltage source, we have connected one voltage source, and we need two for the supply voltages, two here, escape. We need ground here and ground here as well. We need another ground here, I'll tell you why. And then click escape. We need OpAmp 2, then just click enter, escape. It is similar to the inverting amplifier, this control R. We need two resistors here, one here and the feedback here. So escape. Time to connect all this together. This time, last time what we did was we had given the input voltage at the inverting side. This time we'll be giving it to the non-inverting side. That's the only difference. So yes, we have connected everything now. And yeah, oh, I missed this. Again, a big line here, then escape. Quickly we'll add 15 volts here and 10 volts here, and we'll make use of label net here. So VCC, this is our VCC, and need to connect it here. And sorry, not this, minus VCC. This is our minus VCC, and this is our minus VCC. We need another label net for V out. We'll be having our output at this end. It's done, and let's give this some value. Say we need to modify it a bit. So this would be sine wave with offset 0, amplitude as 2, frequency is 1K. Resistor value, let's keep it simple. So 1K, let this be 2K. And the part of adding name here. So you need to repeat the same steps. Copy LM741 bar NS here, Control C, and paste it here so that your OpAmp has a name now. And in order to include the directory, you need to go here, double tap on it, Control A, Control C, and then come here, open spice directive, dot include, Control V, backslash LM741 dot mod, enter. And then I need to name my circuit as non-inverting circuit. This is optional, only if you want your circuit to be neat and clean. So as you are aware, we have applied 2 volts sine wave, and the expected output of non-inverting amplifier would be 1 plus R2 by R1 times the input voltage. So here R2 by R1 is nothing but 2K by 1K, which is nothing but 2, and you are supposed to add 1 with that. So 2 plus 1, 3. 3 into the input voltage, which is 2. So 3 into 2, 6. So the expected output should be 6 volts. The expected sine wave should be in phase with the applied input voltage. Let's check if that's correct. So you need to simulate the circuit before. It's 5M and again 0. So the maximum time step would be 1M. Click enter, place it somewhere in here, and a circuit is ready to be simulated. So run once, we'll change it tile vertically. Just enlarge it a bit. Fine. Our output should be sensed at, our input should be sensed here. So we are getting 2 volts, which is sine wave, and let's check the output now. Perfect. 6 volts, and the output sine wave is in phase with the input sine wave. Moving on, we'll be dealing with inverters.
I just hope that you were able to build the OpAmp amplifiers. Let's go a bit, like we all do have studied from in our engineering about digital logic gates, right? Like the AND gate, OR gate, NOT gate, that is also the inverter gate. So can someone tell me what are these digital gates like further made up of?
Diodes.
Not exactly. Okay, I will just answer that out. Generally, the digital gates that we use so easily are made up of transistors in turn. So we will be studying the working of one such digital circuit, that is the NOT gate or the inverter. So this is how exactly inverter, that is the NOT gate with the help of CMOS NPN and PNP transistors would look like. It consists of a pair of one NMOS and one PMOS, and a common gate input is provided, and the output is taken across the connection between the drain and the source of the NMOS and PMOS respectively. So it is important to analyze how exactly this works, because we know that in an inverter, whenever the input is high, the output is low, and whenever the input is low, the output is high. So it's quite important to analyze how exactly this works. So going on, so we know that the basic knowledge is that for an NMOS transistor, whenever the gate voltage applied is high, that time the NMOS transistor conducts. That is what I'm saying is it acts like a closed circuit, or if we take the concept of transistor as a switch, it acts like a resistor. So it is the opposite when we consider the PMOS transistor, right? So whenever the gate voltage is low, that time the PMOS transistor works, whereas whenever the gate voltage is high, the NMOS transistor works. So let's just analyze this by taking those two cases itself. So whenever you apply a low gate voltage, it is at that time the NMOS transistor, the I mean whatever the gate voltage you apply with respect to NMOS transistor, it won't cross the threshold voltage, because of which NMOS transistor won't be able to conduct anything, whereas the PMOS transistor will be conducting. So it acts like a resistor. As you see in the diagram, whatever VDD we applied to the drain of the PMOS transistor can be sensed as the output, and because of which, since in digital we do have just two values, that is 0 and 1, it is considered to be as 1. Whereas when you take when you apply the input voltage as same as the drain voltage, that time what exactly happens is NMOS transistor will conduct, whereas PMOS transistor doesn't conduct and hence acts like an open switch, because of which there is no flow of current and hence voltage, so your output will be 0. So this is how exactly matches with what we know when we dealt with the digital circuits as well. So now let's get started and let's build it quite quickly, since it's a quite a simple circuit. Okay, so we will be yeah, and one more thing, we will not be using exactly the three terminal transistor thing. We will be using the four terminal one, which also consists of the body thing, and we will be actually making use of FinFETs for this case, because it is very easy to analyze the working of a SRAM cell, because of which we thought of introducing that in the CMOS inverter itself. So I just wanted you to analyze how exactly a FinFET looks like. FinFET exactly is a 3D structure where where the source is distributed across the channel. So this is actually a 3D model, and in LTspice you need to mention the width and the height of the fin. It won't be able to analyze this 3D structure, so we have to do some manual work in order to get the simulations by using a actual FinFET. So for choosing the components, you need to select something known as PMOS 4. It's not the PMOS, actual PMOS which we used to use, which had only 3 terminals. We will be making use of all the 4 terminals, that is along with the substrate. And we will be also making use of the NMOS with the 4 terminal one. And we need to provide a VDD voltage that is connected to the drain of the PMOS, and one more that is the gate voltage. So we will be requiring 2 voltage sources. Okay. Uh, and it is better to analyze the output with the help of a capacitor which is connected to the intersection of the PMOS and the NMOS. So we will be making use of a capacitor. So let's just connect this. Make sure that you connect the gates of the PMOS and NMOS since they are supplied with the common voltage. And I forgot to include ground. And you need to connect the source of the PMOS with the drain of the NMOS, and the drain of the PMOS to that of VDD. And in this circuit, we will be sensing the output across this capacitive load that we have mentioned. So, okay, I just forgot this one. Okay. So this is how barely the circuit looks like. So sorry, I didn't connect the substrate. Substrate you can just PMOS one you can connect it to VDD, whereas the NMOS substrate you can just connect it to the ground itself. Okay, so this is like partially complete. We would be in need of the model files as you have seen when you build the OpAmps circuit. And it was actually a tedious task there, right? You had to download the zip file, then extract it, and then mention it in LTspice. There is also one more way in which you can add the model files, that is by using the spice directive. So we will be sharing the links of both the PMOS and NMOS uh, multi-gate model files in the chat box. This is the file for the NFET, and similarly we'll be having one file for the PFET as well. So moving ahead, we need to copy these two model files into our LTspice software. So what exactly we'll be doing is just copy everything, Control A and Control C, and then go back to the LTspice. So we'll be adding it with the help of the spice directive. So you can just take it here and just paste it. And these files, whatever we have actually included, are not exactly built for the LTspice tool itself. So we need to make a slight modification so that it works for LTspice as well. Just pay close attention. Here we do have something known as dot model NFET level as 72. Just change that number 72 to 9. I hope that you were able to get it, and just press OK. So you will get a whole long list of file. So just drag it and drop it somewhere in your schematic. Similarly, we have to do with respect to PMOS as well. So just copy everything. Within the spice model, just paste it, and don't forget to change the model level. So we have built the thing. Here we need to supply VDD, and this information we will get it from our model files. Here they have mentioned that the nominal VDD is 0.85 volts, so we will be using that itself. So we will be just mentioning it as 850 milli. And here we will be doing actually you just got to know that there are many types of analysis that we can do. So we will be using this one circuit and we will be doing three types of analysis, that is DC, AC and transient. So let's start with DC. So for DC analysis, we will be actually swiping the gate voltage from 0 to VDD, and we know how exactly does that work, right? So in order to swipe that, we shouldn't provide any voltage to the gate, but we will be like uh, actually using it by using the simulation commands. So whatever V is here, it would be okay if you if you just remove it, because it causes issues whenever you run it. Just make sure that you remove that V symbol out there. And as I mentioned, we are using FinFET models, so we need to mention the W by L ratio as well. So we will be taking it as W as 320 and 320 nanometers, and length as 20 nanometers. So make sure that you mention it for both NMOS and PMOS. So I hope that you were able to follow, and we will be including us capacitance with very small value, that is 5 femtofarad. So the circuit is almost ready. For simulation, the first thing what we will be doing will be a DC analysis, a DC sweep. So the source to sweep in my case is V2, and we will be doing a linear sweep itself. So we'll be starting it from 0, and the stop value will be the value of the VDD itself, that is 815 milli, and we are just good to go. So it has been just saved. Sometimes you may not get it here, but it will be saved. So you can just press the run button. I'm really not getting why exactly is this not working. Okay, so we will be just trying with the AC analysis part. So for that, we will be making use of this. We will be modifying this voltage thing. So just right click on this and click on advanced. So here we will be providing a preset DC value. You can provide it as a 425 milli, and since we will be doing AC analysis, we will be making use of small signal AC analysis. Give the amplitude as 1 and phase as 0, and that's just good to go. And in order to make the AC analysis, you have to just go for this, and the sweeping will be the type of sweep we will be making will be a decade sweep, and the number of points you can mention anything. We will be taking it as 10, and we will start it from 1 hertz, and we will be going up to 25 gigahertz. You can just press it as OK, and save this circuit, and you can just run this out. So in order to do AC analysis, it's just enough if you take the output. I mean, if you are able to get the output, it's not required to exactly include the input. So here you will be able to see the AC analysis, where at start it will be like having a very high value, and it drastically drops down. So this is how exactly the AC analysis is done. So with the help of transient analysis, you will be exactly able to view that thing what we studied, like whenever the input is high, the output is low. So for that also, we will be just modifying this one. So instead of the AC or any other pulse, we will be making use of a pulse. So we will just give the basic values with initial as 0. On will be VDD itself, And we won't be introducing any sort of delay or rise and fall time. So and just remove these things also. Okay, so you should be able to see only pulse out here. And you need to modify the thing. So you have to go for simulation thing, and you can go for transient analysis. We will be making it for 100 milliseconds. So just press it as OK. This one will be like automatically deactivated, so you will be making transient analysis itself. So just save the circuit and run it off. So input we have given is a pulse voltage, so it will be like this, and you can analyze the output here. So from this, we can clearly say that whenever the input is high, you are getting the output as low, and whenever the input is low, you are getting the output as high, which exactly matches with whatever we know uh, an actual inverter is. So that is exactly how an inverter works. So now let's move ahead. Okay, so in order to build SRAM cell, that is nothing but a memory element, right? So can anyone just tell me what exactly is a memory in simple English? What comes to your mind when you hear the word memory? Storage. Okay, yeah, that is
Empty space
okay.
to store something.
Yeah, that exactly is why we use memory, and the whole purpose of designing a memory is for. So let's get in. So I just have taken a typical definition, which exactly matches with whatever you have mentioned. With respect to computers, it is used for storing the data or the programs, and it can be stored on a temporary or permanent basis. So let's have a quick look at the hierarchy or the types of the memory that we will be able to find in nature. Generally, we have two broader classes of memory, that is primary memory and secondary memory. So when you make differentiation among these, primary memories are generally faster when compared to secondary memory. With respect to storage, secondary memory offers abundant space when compared to primary memory. So further going down within the primary memory, you have two types, that is RAM and ROM. So RAM is a volatile device, whereas ROM is a non-volatile device. What exactly means by volatile is the whatever information you are like writing in, it will be like able to store it or remember it until and unless you provide a power supply. So whenever there is a power disruption, or if it lacks the power, it will be completely refreshed. So it is not able to retain the information if it loses power. Is a volatile device, and that is what RAM is. Whereas ROM will be able to store the information whatever we have written or read, whatever we have written, even when there is power disruptions. So within RAM also we do have two types, that is SRAM and DRAM. So in this session we will be dealing what exactly is SRAM all about. So an SRAM is a big structure which is again made up of small units, which are also known as SRAM cells. So we will study what exactly is this. So if you look at this circuit, you will be able to make out that this is nothing but what we just dealt. That is a CMOS inverter, right? So these two are this is a pair. I mean, these four transistor constitutes a pair of CMOS inverters, which are like attached back to back. Okay, and this exactly is something that acts as the storage, whatever you just mentioned. What comes to your mind when you hear memory? Okay, so how does this actually works is, say that what if you apply the input as 1 to this end of the thing, this end of the NOT gate, that is the upper NOT gate, so you will get it as 0 onto your right side, right? So then 0 would be applied as input to this. So again, you will get back as 1. So means it is able to store two values. So it is also known as a bistable element. So which is used for the storage, and this itself forms a very simple latch. So latch is the most simplest element which is used for storage, and this latch can be accessed with the help of two transistors. That is, in this case it is M5 and M6, which are also known as access transistors. So by using this small SRAM cell, we can generally perform three operations, that is read, write, and hold. So I will just brief you about what exactly happens in each of these and the lines which are mentioned here. So WL refers to word line. So word line, let us just take it into consideration. So M5 and M6 are basically NMOS transistors, and you know that if there is a very high gate voltage, only then it conducts. So which in turn implies that if the word line, if the voltage applied to word line is high, or that is logic 1, only then you are able to in turn access the latch. I hope that you were able to get what exactly I'm telling. So moving ahead, so whenever the word line is 1, only then you will be able to access this. What happens when word line is 0? So that time your access to this latch is like completely cut off. So because of which it will be in a state of hold, where it will be able to retain the previously stored information. So that is what exactly is hold about. When you want to read something which is already stored in this latch circuit, that time exactly you have to do for read and write is the word line should be compulsorily 1, I mean logic high, so that you will be able to access it. So then you will be having something known as bit line and bit line bar, which is exactly used for the read and write operations. So what happens is, when you take the read operation, so you already have some information which is already pre-stored within the latch, so you have to just take it out. You have to just access it across the bitline bars, and which will be conveyed out what information is stored, right? So whenever the word line is made high, that time it will be like able to access, and it will be like read, I mean it will be put as an output to the bitline and bitline bars, which can be accessed later with the help of other circuits like sense amplifiers. So when you want to write something is, you know that there will be like in some point or the other time there will be some values which will be already stored within the latch. So you need to overpower the latch like with the help of this bitline bars in order to write something new into it. So that is how exactly the write operation takes place. So this is a brief introduction about how an SRAM cell works. So we can analyze this by building one of the model in the LTspice. Okay, in order to build this, we will be, as the name suggests, we will be using 6 transistors, out of which 2 are PMOS and 4 are NMOS. I will be building it up a bit quickly, so just try to catch up with me. You can just rotate the elements by using Control R. So, and you will be requiring 2 access transistors, that is again NMOS. Okay, so this is how typically it is built. So I did mention about the bitline bars, and the word lines. So those are nothing but some sort of power supply. So we will just add them up. So we will be requiring one each for both the bitline and the bitline bar, and we will be requiring one for as the VDD, and one thing for the word line. You can just place this at any point so that we can just connect it by mentioning by adding the labels out. So we have to use the grounds. For these transistors, that is which forms the latch element, we will be connecting it across, whereas in these two access transistors the gate is grounded. So make sure that you add ground to both of these access transistors. So, and let's start connecting it. Firstly you connect the gates of this inverters. Okay, and then we can just connect it up like this. And then connect the drain and source of PMOS and NMOS. So then the gate would be connected PMOS things to the VDD, and NMOS gates would be connected to the ground. Okay, so since this the latch whichever we just went through is known as cross coupled thing, because of which we should ensure that the output of one of the latch is connected as input to the other latch, and vice versa. So in both the things you need to make sure that that connection is well established. So we will just make that out. So the output of this inverter will be from this side. So make sure that this would be connected as input to the other CMOS inverter, and similarly the output of this would be connected as input of this. So moving ahead, so let's just finish up the wirings. So the drain of both the access transistors would be connected to voltage supplies, that is the bit and the bit bar respectively. Okay, I would be requiring one more ground. This was a wrong connection. Here the source should be actually connected here up. So, and the gates of these access transistors should be connected to the word line. So we will make it by using the label net. So this pretty much completes the circuit. So we need to import the model files which we previously did for the CMOS inverters. Make sure that you just copy it down. And make sure that you change the level to 9. So you have finished with this. So we will be keeping VDD as 0.85 volts, or that is also 815 millivolts. So here we will be using two types of supplies. So for the bit and the bit line bar, that is V1 and V2 in my case, we will be giving pulse voltage. So just click on advance and go for pulse. So in this case, we will be mentioning the delays and the rise and fall timings as well. So we'll be starting with 0 and we will be moving until VDD with introducing all the types of delays, rise and falls in terms of picoseconds. And having the time period as 1 nanosecond. So after you enter all these values, just click OK. So you will get it out here. Okay, so the same thing will be done to bitline bar. Since it is complementary, we will be interchanging the first two values, that is the initial value and the on value. So that is done. So and for the word line, we will be making use of a special type of voltage that is known as PWL. PWL stands for piecewise linear, where you can mention the time and your custom time and values, so that the LTspice will analyze it and you will get the output with respect to only those mentioned time and with using the mentioned values. So we will be making use of this. Just type in along with me so that you just don't mess it up. So we can even add many more PWL points. So click on additional PWL points. So you will get it just like a table. So we can add still more. So and just press OK when done. So you should be getting something similar to this out here. So I hope that you were able to follow this. Just a minute. Uh, I was actually doing this in terms of quite in linear manner. This should have been 3 nanos. So just make it as 3, 3.01 and 3.02. So we will get something like this. So this pretty much completes the circuit. And one more thing that we shouldn't forget is adding the aspect ratio for each and every transistor. So it will be the same what we used for the inverter. Just make sure that you add it for each and everything so that you will be able to analyze the circuit. Okay, so this completes the build of this circuit. So the most important thing after building is analyzing how exactly this SRAM works. So you can just click on the simulation and edit simulation. We will be doing a transient analysis. So stop time, we'll be mentioning it as 8 nanoseconds. And just paste it out here. I hope that the circuit is visible. So here we will be doing analysis at various points. Okay, by the way, I just forgot to label the points of wherever we will be doing the analysis. So you can just click on the label net. So the first point we will be taking is Q, and the complementary of that will be here Q bar. So for Q, you will be having it from the bit line. And for the Q bar, you will be having it from the bit line bar. Yeah, and that's complete. So just save the circuit and press run. So the first analysis, what we'll be doing would be to just see that whatever pulse we have applied is right. So you can just place it across the label BL afterward, like somewhere around that label. So it's a pulse voltage, and BL bars should be complementary to this. So that exactly what we have applied. So we will be like doing stepwise analysis. You can add multiple plots within a graph. So that can be done. Just right click and say add plot pane. So when you do this, you will be able to plot multiple graphs within a single simulation. So this is with respect to bitline and bitline bar. So next we will analyze what exactly is happening at Q and Q bar. So these two also will be in complementary to one another as the name suggests. And we will make one more analysis, that is of the word line. So this completes the analysis of whatever we wanted to do. So let us take a quick look at this. So BL and I mean bitline and the bitline bar is just clear. We just applied a pulse voltage and it is exactly the same, which are complementary to one another. But when you see with respect to bitline and the Q, it should had been same. But there is some sort of glitch which we can observe here. So in order to analyze why this glitch arised, we need to know what is happening with respect to word line. So I did mention while explaining that whenever the word line is kept high, that time you will be able to read or write. Whereas when it comes to logic low or zero, that time it will be in hold state. So if you carefully observe here, it is dropping from high to low. That means it is for a short period, that is within this range, it is in the hold state. So when it is in hold state and then it again switches back in order to accept the responses into the latch, you are at that exactly at that point you are like able to see a glitch. So it is caused due to the switching of the word line from hold state to read or write mode. So that is why you will be able to observe these glitches. So if you like look at some other advanced SRAM technologies, like by increasing the number of transistors or maybe any other ways, that time you will be like able to avoid those glitches. Since this is a basic model, you will tend to see those glitches in picture. So this was something what SRAM cell looked like. We did mention a lot about SRAM. So what exactly is SRAM, right? So if you look at that bigger picture in this session, whatever I just taught you a couple of minutes ago, was this small cell which we just built it. So if you look at a bigger picture where you will be able to store multiple amounts of binary information, it will be like arranged in a sort of array in which each SRAM cell could be accessed with the help of row and column decoders. So even the drivers would come into picture, because the transistor switching, like if you look at it in a bigger picture, it is quite slow, because of which they will be using something known as sense amplifiers, so that you will get the outputs much quicker. So in this session, we were able to build a simple SRAM. So if you are much interested, you can even try out building the real SRAM. So that comes to an end to this session. I hope that you were able to learn and even execute the circuits.